I will show how to determine the rectangular components of a three-dimensional force. When the magnitude of that force is known and the directions are given by either two angles, three angles, or 2 points along the line of action of the force. First case we're going to look at is a case where the direction is defined by two angles. Here, the force is given in space by the magnitude and this unit vector lambda, the line of action of which is going to be defined with an angle theta y with respect to the y-axis, and a second angle that's rather peculiar. It is given for a line projected onto the xz plane. That line is the projection of the line of action of the force onto that plane. To obtain the components of this force along the three perpendicular axes, first we get the component along the y-axis, which is given as the cosine of angle theta y times fy. Second component, perpendicular component, is going to be a horizontal component, f of h, which is on this xz plane, and that's going to be the sine of theta y times f. This component fh can be further broken up into components along the x and the z axis. And so to do this, we have to take the cosine of the angle phi and multiply it times f of h to get the fx component. To get f of z component, we multiply the sine of phi times f of h. So those components will be given as f sine theta y cosine phi and f sine theta y sine phi. The vector form of this force is given as f of x in the I direction plus f of y in the j direction plus f of z in the k direction. Next, we're going to illustrate the process by solving two examples. The first example, the angles are given as 30 degrees with respect to the this horizontal plane x, y, and the second angle is given as 40 degrees for that line projected onto the xy plane, and the angles with respect to the y-axis. First thing we want to do is place the coordinate system on point C, move it from point A to point C. The next thing we want to do is break up the 80 Newton force in the vertical direction, or into components along the vertical direction, and a horizontal component on the xy plane. The results are given as f of z equals 40 newtons and f of h equals 69.3 newtons. So again, this is the horizontal component is the cosine of the angle 30 degrees times the 80 newton force. The vertical component, the z component, is 80 newtons times the sine of 30 degrees. Next step is to break up f of h along the x and the y axis. So in the case of f of x, we have f of x is equal to f of h times the sine of 40 degrees. In the case of f of y, we have f of h times the cosine of 40 degrees. And since we already have f of h equals to 69.3 newtons, the result for f of x is going to be equal to 44.5 newtons, and the result for f of y is going to be 53.1 newtons. Now we can write down f in vector form. So f is going to be equal to 44.5 newtons I plus 53.1 newtons in the J direction. And one item, the Z component will be negative because the vector is pointing down, so negative 40 newtons. Okay. The second example is one where we have the angles defined by triangles. So we have, again, the first step is to move the coordinate system from the origin up to point A. So this will be my z-axis. This will be my x-axis. And this will be my y-axis. So we start by finding the vertical component of the force. That would be this. This is F of Z, which will be equal to 500 newtons times 3 over 5, which is going to be equal to 300 newtons. And then the horizontal component, or the component on the XY plane, which is going to be equal to 500 newtons, 4 over 5, or 400 newtons. Now we take that horizontal component and we break it up into components along the X and Y axis. Notice the X component is going to be a negative. So F of X will be the a negative 3 over 5 times the 400 newtons. So this is F of H. And then the component along the y-axis will be positive, and this is going to be 4/5 times 400 newtons, where the 400 newton force is the horizontal component. So F of X is equal to 240 newtons, and F of Y is equal to 320. Finally, we can write down the vector form of this force, and that's going to be equal to negative 240 newtons in the I plus 320 newtons in the J plus 300 newtons in the K direction. Next, we find the direction of a vector given by 3 angles. So if we have our vector living in space, again, the unit vector lambda gives the direction of this vector F. The directions are now given with respect to the x-axis, the y-axis, and the z-axis with these 3 angles, theta x, theta y, and theta z. The component along the x-axis is simply the magnitude of the vector, or force F, times the cosine of angle theta x. That of the component along the y is going to be F cosine theta y, and the component along the z-axis is going to be F times the cosine of theta z. And so there they are, the 3 components. Collectively, the cosines of these angles are known as the direction cosines of the force F. So here's an example. Once again, we want to move the coordinate system to the point where the force is applied. So this is my z-axis, my y-axis, and my x-axis. Notice that the angle for the x is actually with respect to negative x, so we have to get to be consistent. This will be theta x, which will be 120 degrees, not 60 degrees. So now we can find f of x equals f times the cosine of 120 degrees. F of y equals f times the cosine of 60 degrees. And f of z is equal to f times the cosine of 45 degrees. This is 500. This would be negative 250 newtons. This will be 250 newtons. And this is going to be 353 newtons. So in vector form, our force is equal to negative 250 newtons in the I plus 250 newtons in the J plus 353 newtons in the K direction. Apologize for this. So there's the final product. The next item is going to be a vector. The direction is given with 2 points along its line of action, in this case M and N. The unit vector, notice again, is going to be along the line of action of the force. And so what we need to do is find a position vector first, and then find the components along the x, the y, and the z direction. So let us go ahead and find that position vector. The position vector from M to N, we're going to subtract the coordinates of the tail from the coordinates of the tip. And that's going to give us this dx, dy, and dz length. Essentially the length along the x-axis. This length is dx. The length along the y-axis, which is that's dy, and the length along the z-axis is that. So we finally have those lengths. Dx is x2 minus x1, dy is the y2 minus y1, and dz is z2 minus z1. To get the unit vector, we need to do is normalize this position vector Mn with respect to its length. The length we can find using the Pythagorean theorem, essentially the sum of the squares, or the square root of the sum of the squares. And then, so finally, we can write down the force in vector form by multiplying that unit vector times the magnitude of the force. And so it's written out as shown at the bottom of the slide.